Uttam Prabha. Digital India. Educated India.
Welcome to the course Introduction to Algorithms. My name is Saurabh Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. So, this is the second lecture on shortest path. So, in the previous lecture we covered we first start with the shortest path. We discuss the path in a graph between two vertices, and then we discuss what do we mean by shortest path, and shortest path, when shortest path may exist, may not exist. When there is no physical path from two vertex, then there won't be any shortest path. Even though if there is a physical path, but in the presence, if there is a negative cycle in the path, then there may not exist any shortest path. So, that we have discussed in the previous lecture, and we have covered two algorithms there to find the single source shortest path. We have given a source vertex S, and from that vertex we have to find the all shortest path weight, like length of the shortest path. So, that is the delta of S comma V. So, that is the notation we have used, and if there is no shortest path between two vertex, we denote that delta value to be infinity. So, that is the convention we will use. So, first algorithm we have discussed is Dijkstra's algorithm. So, there we assume there will be no negative cycle. So, that means to ensure that we assume that all the weights are non-negative, and then we discuss a general algorithm which is Bellman-Ford algorithm, which can handle the negative cycle. So, there we have no restriction on the edge weight. So, edge weight is any real numbers. So, that is the more general algorithm Bellman-Ford. So, it will give us the all this is also single source shortest path. So, delta of S comma V, or it will report there is a negative cycle in the graph. So, these two algorithms we have discussed, and these two algorithms are both the greedy approach. Now, in this lecture we will first cover the some application of the Bellman-Ford algorithm. So, first we will talk about the directed acyclic graph DAG, and there how to find the shortest path. So, that is we will discuss in the first part, and then we will talk about another application of Bellman-Ford on the linear programming problem. So, there we will see how we can solve a linear constant. So, that is the another application of Bellman-Ford algorithm, and then we will move to the main topic of this lecture is called all pair shortest path. So, like for any two vertex we need to find the delta of u comma v. So, that is the all pair shortest path. So, that we will cover in there we will discuss three algorithms mainly. So, those are basically dynamic programming technique. So, we discuss 3DP algorithm in this lecture. So, let us start with the directed acyclic graph or DAG. So, what is a DAG? DAG is a directed graph with no cycle, as acyclic graph DAG. So, this is an example of a directed acyclic graph. There is no cycle in this in the graph you can take. So, any directed graph with no cycle is called directed acyclic graph, or in short it is DAG. Okay. Now, we have to find the shortest path on this DAG from a source vertex. Now, what to do? We first do the topological sort of the vertices. What is the topological sorting means? Topological sorting means given any two vertex u and v, say given any two vertex, if there is a edge from this vertex to this vertex, then we are basically numbering the vertices 1, 2, 3 up to this. Then if this is numbered by I and this is numbered by j, then I must be less than j. Then I must be less than j. So, that is for every edges. So, given for any edge uv, if this is u, this is v, then f of u, I mean we have to do this, we have to find this function which is a numbering from 1 to, so we have to basically we have to do the vertex numbering. So we are doing this vertex numbering 1, 2 up to, so that this ordering should be followed. This is called topological ordering. So that means if there is a edge from this vertex to this vertex, and if this vertex is numbered by I and this vertex is numbered by j, then I must be less than j. Okay. So that is called topology. So we have to determine a function if, and function means this numbering basically, such that we have to number this vertex such that if there is a edge u to v, then the numbering of u must be less than the numbering of v. So that is what is this. Now for example, if we have this DAG, directed acyclic graph, then how to do this topological sort of vertices? We can use the depth first search. So depth first search and breadth first search we will discuss in the next lecture. So that is two technique to explore the graph. So this we will use depth first search we will use for finding this topological sorting. So for example, so if we start with this vertex as number 1, then if we put number 2 on this vertex, we need to check whether this is an edge. So if we put this must be 1, but 1 we have already used. So this is also connected with this. So this vertex should be a number less than this vertex. So that's why, and there is no other vertex in that ordering. So we give this is 1, this is 2. Then this we can easily give 3, and this we can easily give 4. So if we give 4, then this edge, this is 3, this is 4, the ordering is okay. Even for this also, this is 1, this is 4, ordering is okay. So then we can give the next numbering, this is 5, then this is 6, for that also ordering is okay. Now this is 7, this is 8, this is 9. So this for large graph we will use this depth first search for doing this numbering. Okay. So that is called topological sorting of the vertices. So we do first the topological sorting of the vertices, and that will cost us order of v plus e if we use the depth first search. That is the time complexity for depth first search. Okay. Then after that what to do? After that we have said this is our source vertex. We have to find the single source shortest path. So what to do? We just follow this. So you remember in the Bellman-Ford we have we are doing this for every edges, relaxation step. If you remember, we are relaxing each edge, we are checking this is u, this is v, we are relaxing each edge, applying relaxation step. Now, and there we are doing for each edge, so you have a edge numbering there. Now if you remember the correctness of the Bellman-Ford in the last lecture, so there we have discussed if that ordering of if the numbering is such that in one shot it will be done. So that is basically will be applicable for this case, because if we follow the numbering in the topological sorted one, like the numbering we did for the vertices, then in the one shot it will be done in the one go. I mean in the Bellman-Ford we have a outer loop of j is equal j for order of v minus 1 time, but here for I is equal to 1 we are done, because this if we follow the vertex ordering here, topological ordering. So what to do? We walk through the vertex v in this order. So we just start with 1, then we do this relaxation on this, then we take this vertex, we do the relaxation on this. So this way we just follow we relaxing the adjacent edge of that vertex, and then we go for the next number vertex, and then we do the relaxation. So this is for one go it will be done. So this cost is order of v plus e, because that is the cost. Even we are doing for I mean we are doing for all the edges, so that will cost us order of e. Now if the v is, if there are n vertex and then order of e is bounded by order of n square, then I mean order of v square, so this will cost us order of n square or order of cardinality of v square. Okay. So this is one application. So next application we will discuss the what is called linear programming problem. So what is the linear programming problem? We have given a matrix Ax less than equal to b. So we have given some linear constant. So less than equal to, if it is equal, then we know this is a system of linear equation. So this is the system of linear constant. So Ax less than equal to b, we have to find x such that this is satisfying. So, A is a matrix n by n matrix, and this is a n cross 1. So, there are how many variables are there? So, there are n, this is m by n cross 1. So, n variables are there, and then we have to maximize or minimize some objective function. So, Ct x, so that is our z. So, that is that we have to max. So, we have to find all the solution of this system of inequation, then we have to we can put these values and get the maximum, that is our solution roughly. So, we know that there are few methods to solving this. One is simplex method, which is practical, but worst case it is exponential time. Another one is ellipsoid method algorithm, which is polynomial time but slow in practice. And we have interior point method, which is polynomial time and which can competes with the simplex method, but it is a so it is may not be that good. So, now we will see how we can so only feasibility condition if you consider, like we do not have any function to be optimized, there is no function which you have to minimize, or only you have to find x such that this is satisfying. So, that problem is as hard as the original ordinary linear programming problem. So, there is no, so we will mainly consider on this feasibility problem. We have some system of this is inequalities, and then we have to find the x which satisfy that inequalities, and in our case the inequalities are of particular form. So, that is called linear system of different constant. So, in this case the matrix A is having our inequalities are of this form. We have only two variable in each inequation. So, x1 minus x2 less than equal to 3, x2 minus, so only two variables. So, each rows of A contain only 1 minus 1, remaining are zeros. So, that will give us this type of system of different constant. So, we have to solve this system. So, we have to find x, this x1, x2 and so on, which satisfy this system of different constant. So, that is the problem. So, that problem will solve this using the Bell-Manford algorithm. So, for Bell-Manford we need to bring a graph. Now, the question is how we can bring a graph from this inequation. So, we can think for each inequation can give us a h. So, how? So, this is we can think for this is a general form in any inequation like xj minus xi is less than or equal to wij. So, this will give us a graph like this. Yeah, so this will corresponding to a vertex xi or vi if you like to use v notation, and this is vj, and this is less than this weight of this is basically weight of the edge. So, this will corresponding to this and this will corresponding to this. So, every inequation, so this means we have a edge over here. So, given an inequation we can form a graph. Okay. So, that is the idea. So, we can just have a graph, and once we have a graph, then we have, and the size of this matrix has dimension v order of v cross order of v cross order of v. Now, the question is, so we have a graph, now we can think for applying Bell-Manford. Now, if this graph is having a negative cycle, then this system is not consistent, that means there is no solution of this system. So, that is called unsatisfiable. So, if this constant graph means this way, we take every inequations and we form this part of the form these nodes, and we connect this, we make a edge, and weight of the edge is basically this value. Okay. Now, if this graph constant graph contain a negative weight cycle, then the system of this difference is unsatisfiable. That means there is no solution of this system. So, how to prove that? Suppose this graph has a negative cycle, negative weight cycle, and that is starting from V1 to V1. So, V1, V2, Vk and V1 come back, this is negative, this weight of this is negative. So, this is W1, 2, W1, W2, 3 like this. So, total weight is negative. Now, this is a constant graph, part of constant graph. So, this will give us this part of the inequations. So, constant. So, the x2 minus x1 is less than W12, this is W12 and then W23. So, x3 minus x2 is less than W23 like this. Now, if you take the sum of this, then this will cancel out and x1 cancel out, there we have a 0 and here we have all the weights of this, and this is negative because this is a negative cycle. So, this is negative and this is 0. So, that is a contradiction. So, that means there will be no solution, no values of xi which can satisfy this constant. So, that is the proof of if this constant graph is having negative weight cycle, then this system is unsatisfiable. Now, if there is no negative cycle in this graph, then these constants are satisfiable, then the system has a solution. And how to get the solution? Again we will use the Bellman-Ford to get the solution. So, let us first consider the original graph. This is the graph of this constant graph coming from this inequations. Now, we add a new vertex in this graph, okay, and we add this vertex in this graph and we introduce all this new edges which is connected from this vertex to all the vertices in the original graph. So, V1, V2 like this. So, these are basically all the vertices, all the edges we are introducing. This is from all the other vertices and this weight of this vertex we are putting to, weight of this edge we are putting to 0. Okay. So, then if the original graph was having no negative cycle, this graph, this new graph will also have no negative cycle because we have only introduced 0 weight edges. So, that cannot make the graph negative weight, that cannot make any negative weight cycle. Okay. So, this has no negative cycle. So, now if we apply the Bellman-Ford on this graph. So, if we apply Bellman-Ford, what it will give us? Since there is no negative cycle, so it will terminate and it will converge and it will give us delta of s comma vi for all vi, s comma v for all v. So, ultimately it will give us all the length of the shortest path or weight of the shortest path from S to all other vertices. Now, that we will use to get the solution. So, how? Now, we are claiming that S comma Vi is xi are the solutions for this constant. How to prove that? Now, we consider two vertex. So, this is basically one part of this constant graph. So, now we take this vertex S. Now, we take this shortest path, this is delta of S comma Vi and this is delta of S comma Vj and this is Wij. And what was the constant? Constant was that xi minus xj minus xi is less than equal to Wij. Now, we know the triangular inequality. Triangular inequality is telling the shortest path between S to this must be less than shortest path between this, shortest path of this must be less than shortest path of this plus this. Now, this is shortest path and this is one path. So, shortest path must be less than this weight of this path. Weight of this path is delta of S comma V plus Wij. So, so S to Vj, the delta must be less than equal to weight of any other path. So, the delta of S comma Vj, which is the shortest path, must be less than delta of S comma Vi plus Wij. So, this is basically our solution of this constant. So, these deltas are nothing but the solution of this constant. So, that is the proof. So, now not only this will give us a this feasible solution, this will also give us a can maximize this x1 plus x2 if we have the optimal, if we have to maximize this x1 plus x2, our C is all zeros or all ones. So, that can maximize this. So, this you can take an exercise, even it can minimize this maximum of xi minus minimum of xi. Okay. So, this you can take. Now, let us come to the main part of this lecture, all pair shortest path. So far let us just recap what we had discussed. We have discussed two algorithms, Dijkstra's algorithm and Bellman-Ford algorithm. All are single source shortest path and all are greedy approach. And for Dijkstra's we assume the non-negative edge weight in order to avoid the negative cycle. Now, if we have to find the all pair shortest path, that means between any two vertex we have to find delta of uv for any two vertex, not only for a source vertex. Okay. So, that can be done if we assume the W weight is non-negative, then we can apply Dijkstra's order of V times. So, we first choose a vertex, then we apply that is our source vertex, we apply Dijkstra's, then it will give us the all the weight of the shortest path of the all the vertices from that particular vertex, and this we run for V times, or we can apply Bellman-Ford V times, so that way. We will see this time complexity. So, for that let us just recap the time complexity of Dijkstra's algorithm. So, Dijkstra's time complexity was of this form. Now, if we use the array, then this is the total time we have discussed, and if we use the binary heap, this time we have already discussed. Now, if we use the new data structure which is called Fibonacci heap, then this is the cost for extract mean and this is the cost for decrease key, amortized cost. Amortized cost we will discuss in the future lectures, and then this is the worst case time complexity, order of E plus V log V. We will take this time complexity for Dijkstra's algorithm for single source shortest path. Okay, so Dijkstra's this is the time complexity, order of V E plus V log V, and this is the time complexity for Bellman-Ford, order of V into E, and this is the time complexity for directed acyclic graph. So, just the one run of Bellman-Ford, that is the order of V plus E. Now, for all paired shortest path, if we use Dijkstra's, provided there is no negative cycle, then we have to run V times. So, it will be order of VE plus, these are order means these are the cardinality of V into cardinality of V. So, if the size of V is n, so that means if there are n vertices, if the cardinality of this vertex size is n, then this will be, and then E is the order of V square. The cardinality of E we know it is basically big O of n square, and it is big omega of n because connected graph, and this is the complete graph. So, this is bounded above. So, then this will be basically order of V square, order of n square, and this can be n cube also if this is this bound. So, anyway, this is n cube plus this, and but if we use the Bellman-Ford, we will see that then it is more. But today we will discuss three algorithms which are not greedy, which are dynamic programming technique, because we have seen the for shortest path the hallmarks are there for dynamic programming, that is the optimal substructure, and overlapping sub problems are also there. So, that then we can use the dynamic programming technique for doing that. Okay, so let us start with the first algorithm of DP. Okay, so suppose V is there are n vertices. So, we can number the vertex 1, 2, 3. So, V1, V2, Vn basically. So, for simplicity we can take 1, 2, 3. So, vertex are numbered by 1, 2, 3, 4 up to n. There are n vertices. Okay. Now, we define this, and suppose these are the input. We have a diagram which is G, V, comma E, and V is this vertex set, and we have a edge weight which is W, which is V, which is E to R. This will be E. So, there is so this will be E to R. So, this is set up, this is the edge weight E to R, and output will be all pair shortest path. So, given, so this is a delta of I comma j. So, given any two vertex, so you must get a delta if there exists, otherwise it will be infinity. So, this is vertex I, vertex j, any two vertex, because vertex are numbered from 1 to n. So, this is the path say, This is our delta of I comma j, and this is for all I and j. For given any two vertex, we should, so for all of, so this is basically we can write in a matrix form. So we know there are n vertices. So this is 1, 2, 3 up to n. So we can have here 1, 2 up to n. So what are the, so matrix is basically delta of ij. So delta of ij is the, so we have a ith vertex over here and we have a jth vertex over here. So this is jth vertex. So this entry, this is the delta of I comma j. Okay. So that is the matrix form I comma j. So this is for all I and j. So basically this is a n cross n matrix. This is a n cross n matrix. So that will be the output. So we have to output the all pair shortest path. So for any two vertex I and j, we need to get the delta. It could be infinity also if there is no shortest path, depending on whether there is a physical path or it may have the negative cycle in the path. So then there won't be a shortest path. So basically this matrix we need to output. This is a delta matrix, big delta. So this is a n by n matrix. So we need to output this matrix. So given so this is the input. We have a graph, directed graph, and we have edge weight. These vertex are basically, there are n vertices V1, V2, Vn. For simplicity, we are taking 1, 2, 3 up to n. So just then we have to find this delta matrix, which is basically the delta of I comma j. So that is basically between any two vertex, the shortest path we have to find. So this matrix. So this is delta 1 1, delta 1 2, delta 1 j, delta 1 n, first row, second row, like this. So this is the all this matrix we need to get, this n by n matrix. So now the question is how we can do that. So that is the all pair shortest path problem. So we have to get some algorithm for that. So if we think of whether we can use the Bellman-Ford on this. So because Bellman-Ford we know it's a general, because here we have no restriction on the positive and non-negative weights. Okay, so we can run the Bellman-Ford and Bellman-Ford we can run for, we take a vertex I. So basically for I is equal to what is the code? Basically for I is equal to 1 to n, we run the Bellman-Ford. When you run the Bellman-Ford, we need to give the source. So source is basically I. This is our Bellman-Ford algorithm on this I. I is the source, and this we run for, and this is also the input. The graph is also the other input, and for every time, so I is the input. So this we run for n times. So each time it is order of v into e. So there are v vertex. This is the size of v. So n is basically v, cardinality of v. So this is a v square into e. So now if we know e is order of v square, so this is basically order of v to the power 4. So n to the power 4 times. If this is a dense graph, dense graph means if it is a not sparse graph, then e is order of v square. So this will be order of n to the power 4 algorithm. So we want to do better. We want to see, we want to apply the, this is greedy, we want to apply the dynamic programming technique for this. So to apply dynamic programming, we use this notation Dij. Dij is basically Dij m is nothing but we are at ith vertex and we have to go to jth vertex. So this is I and this is our j set. Then there are many there are paths from I to j. It could be infinity also if there is no shortest path, if there is no path from I to j, then there is no question of shortest path. So Dij m is telling we have to go from I to j, the weight of the, we have to consider all the path from I to j such that we use at most m edges in the middle. So when you go from one vertex to another vertex, we have to visit some edges. So this is this is first we visit, say, if this is I, then we visit one vertex. So this is one edge. Edge means direct edge. This is another edge. So this we count the number of edges. So we consider all the path where number of edges is at most m. So that this m. So we are allowed to take at most m edges. So then we count the number of edges. Number of edges is must be less than equal to m. Okay. And among those paths, whichever is the shortest path, then weight of that shortest path is basically di m. That is the notation. Is this clear? So notation is very straightforward. We consider the path. This is the weight of the shortest path from I to j, vertex I to vertex j, that uses at most m edges. So in the middle we must use number of edges, because we have to, I mean, path means it consists of some of the edges. We follow the edge and we go from one vertex to another vertex. So we count the number of edges. So number of edges must be less than equal to m. So at most m edges we must use. So that is the definition of di m. So what is the use of this? I mean, what we are looking for? We are looking for delta I comma j. So basically we are looking for delta of I comma j, and shortest weight of the shortest path from I to j. Now what is the use of this dij? I mean, how dij is related to delta? So if there is no negative weight cycle, then delta has a finite value, and then if there is no negative weight cycle in the path, that means what is the intermediate, I mean the how many edges it will be used in any path? At most n edges or n minus 1. So it is basically dij n minus 1 if there is no negative weight, if shortest path exists, then this is the relationship. That is why we are looking for dij. We will go for dij up to n minus 1. Okay, so this is we are defining for m is equal to, this is a we will use this formula, we will prove this formula. This formula will give us the algorithm. So that is the dynamic programming bottom up technique. So first of all we need to prove this dij. So basically delta of ij is nothing but dij n minus 1, because if there is a shortest path, then there will be no negative cycle. So if there is at all a cycle, that will be positive cycle. So positive cycle on the path, we will not hop on that. So that all the path will be the simple path. So there will be no cycle in the path. So there will be no repetition in the vertices there. So that means number of edges will be maximum n minus 1 for this delta of I comma j. Okay, now let us prove this. This is the formula we are going to. So what is the dij 0 then? Dij 0 means, so we are at I, so we have to go to j. So we are at I, we have to go to j without seeing any path. 0 means there will be, without seeing any edge. So that means if there is a self loop, so it is 0 if I is equal to j, because there is no question of self loop. If self loop also there is a path, that is there is a edge. So if I is equal to 0, I is equal to j, that means we are at II, dii is 0 is 0, because we are at I, what is the best thing? We will be at I, that is the shortest path, okay, if there is no negative cycle. Otherwise it is infinity, because we cannot, without visiting any edge, we cannot go from one I to another j, where ij are different. There is no question. We need to have at least one edge, direct edge. So that is why it is dij 0 is infinity. So this is the initial value of dij, and for other value we will use this formula. So dij m is basically minimum over k, this k is dik m minus 1 plus d plus akj. Where is the A matrix? So this is the adjacency matrix. So if the adjacency matrix means if there is a, this is the basically weight of that path. So aij is basically, we have to define this aij. So aij, so this is Adjacency matrix means if there is a edge from I and j, and here we are defining this as a wij. If there is a edge, then edge is associated with a weight. So, that edge weight is our Aij. So, this is how we define Aij. So, this Aij. So, this is the weight of the path I to j. So, Aij is the adjacency matrix, where in the adjacency matrix we have 1 or 0, but here instead of 1 we have this if there is a 1 means there is a path from I to j, direct path, direct edge, and weight of that edge is wij. So, that is our Aij. Okay. And that is our, this is the formula we need to prove. So, let us prove this formula. Now, this is our claim, Dij m is nothing but minimum among all k's, k is running from 1 to n. So, 1 less than equal to k less than equal to n. So, this k value. Okay. Now, anyway, this will come. So, this is how to prove this formula. So, we can just prove by this figure. So, we are at I, we need to go to j. So, these two are vertices. Now, there could be direct edge to j. So, there could be incoming edge to j, and this could be from other vertices or from same vertex j. From same vertex means there could be a self loop over here. Now, if we have to visit m Dij m number of edges to go from I to j, now we already have a direct edge from this vertex to this j, even for self loop. Then, so how many, so from I to these vertices, what is the number of edge we are allowed to visit? That is less than equal to m minus 1, because total is m. We have already have a edge, direct edge. So, then from I to k, I to this k, say this is kth vertex, say k is varying from 1 to n. So, any vertex could be there. So, depending on the how many direct edge is there to j. So, then in this path from I to these vertices, in this path we are allowed to take maximum m minus 1 edges, because total has to be at most m edges, that is the Dij m. So, in this path we are allowed to take at most m minus 1 edges. So, we consider all such weight of that path. So, this weight, that is Dik m minus 1 plus this direct edge Akj, this is Wkj, that is nothing but Akj. So, this is the weight from I to j if we follow this path, and among this which is the minimum, and this is the direct because this k could be j also. If k is j, then there is a self loop over here, that is Ajj, and this is the, we go here and we use this self loop. So, this k varies from 1 to n, depending on how many direct edge is there. Okay. So, this formula is clear, straightforward from this. So, we consider all such path, among this which is the minimum. So, minimum 1 we will take, and that minimum 1 is Dik. So, this will give us this algorithm. So, we can just how to get these values. So, this is basically the relaxation step. So, we have a initial value, we know the initialization of Di0, then we have a loop over here, so this we can use m minus 1 over here, and this is m, but anyway these are just the temporary variable. So, if di the value whichever having is greater than Dik m minus 1 plus Akj, then we must update that. So, that is the relaxation sort of we are doing. So, this is the code. Now, we can think this as a matrix multiplication. So, how? So, we will see that. So, if there is no negative weight cycle, then we have then this Dij n minus 1 is basically our delta ij, because that is what we have already seen in the last slide. So, this is basically there will be no negative cycle, means if there is at all a cycle, that will be positive. So, we will not hop there. So, every shortest path is a simple path. So, we will go from I to j with the simple path. So, there will be at most n minus 1 edges in the middle. So, this is the convergency of that. So, delta of ij will be Dij n minus 1. So, that now we consider this Dij in a matrix form, and we will see how this will be related with the delta, I mean this matrix. So, this we want to see in a matrix multiplication way, this, because this is nothing but k is varying from 1, k is varying from 1 to n. So, this will give us a matrix multiplication formula. How? So, let us recap the matrix multiplication formula. If we have two matrices A B, A is n by n, B is also n by n. So, Aij, Bij. So, these two matrix. So, what is the product matrix? This is also will be n by n, Cij is the ijth term, and that is basically the inner product of ith row of A and jth column of B, and that is summation of Aik Bkj. And we know this will take order of n cube for standard matrix multiplication, or if you use the station it will reduce little bit over here in the exponentiation. Anyway, we will take the order of n cube time it is taking. Okay, now how we can relate this with this, and we can think this is nothing but a matrix multiplication. So, for that let us map the operations, like this is we are doing minimum, and here we are doing sum, and this is also for I is equal to, I mean for k is equal to 1 to n, and this is also for k from 1 to n. So, if this sum we think of a minimum, and this plus we think of this product, then this is nothing but a matrix multiplication between this di, this is nothing but dik m minus 1, and this is akj. This Bij is basically Akj. So, we just consider this minimum as this sum plus, and this dot as this plus, and this will be the matrix multiplication, which is this way we can think. So, this if we take this as a matrix, this Dij matrix, what is the matrix over here? So, if we have a matrix D, which is a D matrix, D of say you can take M is equal to Dij, ijth of M. This is how we define this matrix. Okay. So, this is also n by n matrix, because this Dij is defined for all I and j. So, this is our n by n matrix. So, similarly, we have capital D m minus 1, capital D m minus 1, and that entry is, so D m minus 1 is nothing but the matrix Dij's. This is the ijth entry of that matrix. This is m minus 1, okay, and this is n cross n matrix, and we have A matrix over here. So, this is if we follow that, this is nothing but D to this matrix into A, because this is this we are connecting with this operation minimum and this plus, minimum and this plus. So, this will be the basically the matrix operation like this, very nice. So, we got we relate this to a matrix operation, where the identity matrix is nothing but this, and D0 is the Dij 0, which we know this one, okay, and this will serve as an identity matrix. And the matrix multiplication has some rule. This is a if we have to use the matrix multiplication properties. So, this must be associative with the real number we know, and it for algebraic structure or closed semi-ring. So, all this we are assuming these are happening over here with these two operation minimum and plus, and then we can have this matrix multiplication Dij m is this. Now, this will give us a, so we are looking for Dij n or n minus 1, sorry, D to the power n minus 1, that will give us all the dij's. So, that is nothing but, so what is d0? d0 is d1, d1 is d0 into a. So, a, this is identity matrix, so this is a. So, d2 is d1 into a, we are using this formula. Okay. So, this way, so dn minus 1 a to the power n minus 1. So, this is nothing but our delta ij. So, how much time it will take? It will take, because there are n multiplication and each multiplication will cost us n cube. So, this is order of n to the power 4, which is not better than the Bellman-Ford n times. So, we want to do it order of n cube algorithm. So, that is the next algorithm, next dynamic programming approach, that is called Voigt-Warshall algorithm. Or we can use this, even this algorithm we can use. So, that basically we have to get a to the power n minus 1 or a to the power n. So, we can think this is a matrix multiplication way. We can improve the matrix multiplication algorithm by this squaring. How many? So, we compute a to the power 4 like this. So, this way how many squaring? Order of log n squaring. So, each time we are spending n cube. So, this is nothing but n cube log n. Okay. And to detect the negative cycle, we just check the diagonal element of this, and if there is a negative number, then it is there is a negative cycle. But we want to do it in order of n cube. So, that will give us the that will be done by the next algorithm, which is Voigt-Warshall algorithm. So, Voigt-Warshall is also a dynamic programming algorithm, but it is faster than the previous one. So, here we define new notation Cij_k. So, Cij_k is the shortest weight of the shortest path from the node I to j with intermediate vertices belongs to the set. So, that means if we, so when we go from I to j, we will visit some vertices. So, this vertex number should be less than equal to k. So, we should not see any vertex whose number is more than k. So, that is the Cij_k. So, all the vertices we visit in the middle. So, here there is no restriction on the edges, we have only the restriction on the vertex numbering, because vertex are v is from 1 to n. So, our vertex set is 1 to n, if you recall. So, v is our vertex set 1, 2, 3 up to n. This is our vertex set. So, we go from ith vertex to jth vertex, and in the intermediate vertex we visit, these are number basically less than equal to k, and we consider all the such path, and among that path which is the minimum weight, that is our Cij_k. So, Cij_k is the weight of the shortest path from the vertex I to vertex j with the intermediate vertices belongs to the set. So, there will be no vertex whose number is more than k. So, all the vertex we visit in the path from I to j must be less than equal to k. So, that is the restriction, and among all such path we take the minimum one, and that is our Cij_k, that is the weight of the shortest path of such restriction. Okay. Now, what is Ci0 then? Ci0 means, so we are, so there is no vertex number from 0, because vertex number start from 1. So, Cij0 means direct edge. So, that means from I to j we have a direct edge. So, that is nothing but from I to j. So, we do not want to see any vertex exist, because vertex number are from 1 to n. So, Cij0 means we are not allowed to see. So, that is the direct edge from I to j. So, that is our Wij or Aij. So, that is the way Cij0 is, that is the initial case or base the initial value of Cij. And why we are looking for Cij? Because we know if we get all the Cij's for all k, then that is nothing but this is not d, this is delta. So, that is the delta ij n, because n is our vertex is up to n, vertex numbering. So, Cij n is nothing but delta ij, because n is the maximum number vertex. So, that is the for all vertices. So, that is delta ij. So, that is ourCijn. So, good. So, now we want to have a formula on this Cij, so that we can use that as a dynamic programming. So, this is the formula we are going to use. Cij k is the minimum among Cij k minus 1, comma Cik k minus 1 and Ckj k minus 1 plus. So, how to prove this? So, proof is straightforward from this. So, we want to go from I to j. So, it may happen and we do not want to see in the path the vertex whose number is more than k. So, that means all the vertex, intermediate vertex number will be less than equal to k. So, there are two possibilities. One is there will be no vertex of number k. So, that is our Cij k minus 1, that is the weight of the shortest path from I to j with the vertex number maximum k minus 1. So, all the vertex are from 1 to k minus 1. That is one possibility. There is no kth vertex in the path. So, we take the all the path among that. So, this is the shortest path Cij k minus 1, and there is a possibility is that there are kth vertex in the path. So, then what we do? We go that kth vertex, we go Cik, and in the intermediate path we do not see any kth vertex. So, that is basically Cik k minus 1, and from k to j Ckj k minus 1. So, this to sum will give us if we have a kth vertex in the path, and if there are more kth vertex in the path, then there will be self loop over here cycle, and that cycle, if the shortest path exists, that cycle will be positive cycle, and positive cycle we do not need to bother about, we will not hop there. So, we will just take this one. So, in any case Cij k is either this one among these two, whichever is the minimum. So, this there is no kth vertex, or if there is a kth vertex, then this path plus this path. So, minimum. So, that is the formula for Cij k, and we will use this formula to have a algorithm, that is basically the Voigt-Warshall algorithm. So, this recursion will give us a formula. So, we have to find all Cij's, and that will give us Cij n will give us delta ij. So, this is the formula. So, k is equal to 0 to n, we have Cij, and this will be m minus 1, and this will be k minus 1 k, but we can omit the superscript, because these are basically the temporary variable we are storing, and this is nothing but the relaxation. So, we update this if the Cij Cik k minus 1 plus Ckj k minus 1 is less than the previous value, I mean is better, is less than the previous value, then we must update this at the kth level. So, that superscript we are omitting, but you can use that. Okay. Now, this is the algorithm which is called Voigt-Warshall algorithm. Now, what is the time complexity of this algorithm? This algorithm is having 3 loops. So, and we have having this relaxation step. So, this is order of n cube algorithm. This is very simple code and very efficient in practice. So, this is a dynamic programming technique, and this is basically bottom up. We start with this is the initial value Ci 0, and then slowly we will go up with Cin, and that will give us. Okay. Now, we will see some application of this dynamic programming, this Voigt-Warshall on what is called transitive closure of a directed graph. Okay. Suppose we have a directed graph with no edge weight. Okay. We have just a diagraph or directed graph. We have a G, which is V cross E, and this is a directed graph. There is no edge weight. Now, we know the transitive closure. Transitive closure means we suppose we have two vertex I and j, Now, transitive closure of this is denoted by Tij. Tij will be 1 if there is a path from I to j visiting some, because this is a directed graph. So, we can follow the edges, and if we can go from I to j, then this value of Tij will be 1. So, the Tij is 1 if there exists a path from I to j. So, there is no question of shortest path over here. it's just a path. So if we can reach from one node to another node, so that is the question. So there are many applications on this. So if we can reach from, say there are programming in the programming language, if we can reach from one code to another code, so there could be many applications on this. So basically it is a directed graph with no edge weight. So only thing, we define this transitive closure Tij is 1 if there is a path from I to j. Otherwise, if there is no path, then it is defined to be 0. Okay. Now question is how to find this Tij. So this is for all I and j. If we consider this as a matrix, so this is a n by n matrix. So how to find this Tij's? So for that we will use the Floyd-Warshall algorithm. So we will just use this notation, this logical OR and logical AND as a minimum and plus, and for all each edge we have a 1. We just assign the weight to be 1. Okay. So that Wij, if there is a direct edge from I to j, we assign 1 and we apply Floyd-Warshall, and this will give us this logical, because this will be the shortest path, but here we do not bother about shortest path, we only need the path. So that is why we will use this logical operation, it will be either 0 or 1, this ANDing and ORing. So the idea is to just to use the Floyd-Warshall, instead of minimum we will use this OR gate, and in plus we will use the AND gate. So this output will be 0 or 1, and this will be, since we are running Floyd-Warshall, this will take order of n cube time to get the matrix Tij n cross n. Okay. So now we will discuss another algorithm for finding the all pair shortest path. This is called Johnson algorithm. So before that, let us so Johnson algorithm is nothing but applying the Dijkstra's algorithm v times, because Dijkstra's algorithm we have seen, it is if you remember, it is the better one than the Bellman-Ford, in the time complexity sense. Okay. Now, but Dijkstra's we have a restriction over there, because it cannot handle negative cycle. So we take the every edges will be non-negative, but here we are dealing with general graph. So this weight function is general, so it could be negative also. So we want to make it positive, like we want to change the, we want to reweighting the edges, so that we will have a positive weight. So how to do that? So for that we will label the vertices, h is a function, we label the vertices and we reweight this edge for every edge by this is the new weight of this Wij, Wuv is an edge. So it was Wuv plus Hu minus Hv. Okay. So then what is the path weight? Path length is basically this one, P of P is a path, then what is the weight of this path? Is sum of the edge weight. Now if you do this sum and if you put this value, it is nothing but Wp, the original path, plus this. Now this one we want to be positive, I mean this one to be positive. So we want to choose this h in such a way that this is greater than 0. So that means Wv minus Wh must be less than equal to Hv minus Hu must be less than equal to Wiv. So that we want to find this h. So you want Hv minus Hu must be less than equal to Wuv, and that we can do it by Bellman-Ford, because this is a system of constant graph, a constant linear constant. So this is, we can construct the graph, and that can be using Bellman-Ford we can get this constant, okay. Or we can determine a negative cycle exists. If negative cycle exists, there is no question of shortest path, even using the Dijkstra's also. And this can be done in order of v into e time, because we are applying Bellman-Ford to get this h. So once we got this h, then we have a new weight of new edges weight, and that will be positive. So once we get this positive, we can run Bellman-Ford and on v times, and this will be order of v plus v square this, because one Bellman-Ford will take order of e plus v log v. So v times we are doing, this is cardinality of v. cardinality of E. Okay. And this reweighting again we have to do, because this we have to get back this formula, because we will get the weight, this is reweighting we have to do, because we are looking for the weight of WP. We got the weight of W hat P. So, this reweighting also we have to do, and that will cost us order of V square time. So, total cost is, this is the cost for this running the Bellman, this is the dominating cost. So, this is called Jensen algorithm, which is the idea is to use the Bellman Dijkstra's algorithm, which is better than Bellman-Ford. So, let us conclude this lecture. In this lecture, we have discussed more on shortest path, like we discussed some all pair shortest path algorithm. Here we have discussed 3 algorithms, and then we compared their time complexity. Also, we have discussed some of the application of Bellman-Ford algorithm in the initial part of this lecture. Thank you.